Okay, so welcome back. We have seen, we stopped last time with the Cayley-Hamilton theorem. Today we will start with, I believe, the minimal polynomial. So we've already seen the characteristic. What just happened here? How is this portion? It's very bad. Okay. And we've seen that, and then we've seen the Cayley-Hamilton theorem. That was where we stopped last time. So today we will talk. Sorry, this is not the eraser. This is the eraser. Today we will talk about the minimal polynomial. Of either a matrix A or of a transformation T. So either way. I think I'll start with the minimal polynomial of a matrix A. Okay, so there's basically nothing much to say. Okay, so what we have seen is that the characteristic polynomial kills A, right? So we have seen, so by the Cayley-Hamilton theorem, if you look at the characteristic polynomial and you evaluate it at the matrix A, then you know you get the zero matrix n cross n. Right? Okay. So now the point is that means that there is at least one non-zero polynomial which kills A. So in particular, if you multiply this polynomial by any other polynomial, so in particular, for all, let's call this q of x belongs to fx, meaning for all polynomials, if you look at px times pa of x times q of x, if you take this polynomial and evaluate this polynomial at A, then you get pa of A, which is 0, times some other matrix, which I don't care what it is, and I always get 0. Okay, so this is so therefore from one polynomial, I've just gotten a large number of polynomials, in fact, infinitely many of them, all of which kill A. So let's look at all the set of polynomials which kill A, not just the multiples of PA, which of course kill A, but maybe there are other polynomials that kill A. Can we describe all of them? So question, can we describe, so given matrix A, can we describe all the polynomials or the set of polynomials given, so you know A belongs to f to the n cross n, describe all polynomials, describe the set P in fx such that P of A equals 0, n plus 1. Okay, this is clearly, I mean, so this is set of all polynomials which kill A. Okay, now the interesting thing, okay, so let's see what this does. So what is this set? So as we said, so if two polynomials kill A, then of course their sum kills A and scalar multiple kills A. But in fact, if any polynomial kills A, then any other polynomial times it also kills A. When evaluated, A also becomes 0. So this set is therefore something called an ideal. So this set is not only closed under addition and multiplication and so on, plus and times and scalar multiplication. So if it's closed under addition and scalar multiplication, this being a vector space, the set here is already a subspace of the vector space. So it is not just a set, it is a vector subspace. Okay? It is also an ideal. This is sort of you don't need to pay attention to this if you have not taken algebra 1 or something, or are not taking algebra 1. But for those of you who are, you know what an ideal is in the ring Fx. It's an ideal of the ring. But the point is, this ring is something called a principal ideal domain. And that means that every ideal is generated by one thing. Every ideal is principal. It is generated by one element. Meaning there is some polynomial, not PA, but some other polynomial, I'll call it P min of X, such that every polynomial in this set is divisible by P min. So there's there's one polynomial of smallest possible degree, such that P min of A is 0. So the min is because of minimal degree. P min of A is 0. And every other polynomial such that P of A is 0 is on the form Q of X times P min of X. And that is right. So this implies, so the PID implies that that this ideal, let's give this ideal a name, let's call this I. This set I is, so this ideal equals, literally equals P min of X times Q of X, such that Q is in Fx. It is every single multiple of P min of X. So basically there is some polynomial P min such that P min of A is 0, and the moment P min of A is 0, the same kind of thing, P min of A times Q of A is automatically 0 as well. Right? So there is some such polynomial. I'm just telling you this based on sort of take my word for it, but now we will actually prove this statement. That's the point of this next result. We will prove the existence of this thing for some non-zero, I don't need to say that, monic. Monic means that the top degree term has coefficient 1, the top monomial. Polynomial P min of X of smallest degree. Right? Every other polynomial that kills it is divisible by that, so its degree is at least as big as the degree of P min. This is the unique smallest degree. Of smallest degree, of course, of smallest degree in this ideal I. Okay, so that is the statement. Okay, so this ideal I equals the set P min of X times Q of X, where Q runs over all possible elements of this polynomial ring for some non-zero monic polynomial, P min of X of smallest degree in I. Right? So and now let's make that formal. So I stated this. I'm just telling you, take my word for it. But now we will prove it, and the proof is because of something which is even more basic than a PID. It's called a Euclidean domain, which means it's a domain where you can do long division and you can get quotients and remainders. And we know that for integers you have the same property, and for polynomials you have the same property. You can do long division of polynomials and get quotients and remainders. Once you know that, this is actually not hard to prove, and so let us prove it. So of course, which is not surprising, this P min is going to be called the minimal polynomial. But now let me write this statement down formally as a theorem and then give you the definition of the minimal polynomial. Using probably a blue pen, if I can see. Okay. Okay, great. Theorem. So again, usual things given n, f, and the matrix A, which is in F to the n cross n. There exists a unique polynomial, and now literally unique, which is monic. Okay. There is a unique monic polynomial such that there exists a unique monic polynomial the monic word is by this unique P min of X such that it satisfies this statement. such that P of A equals 0 if and only if P min divides P. Okay, so such that P of A equals 0 for some polynomial in Fx, if and only if the polynomial P min divides the polynomial P. That's it. That's the statement. Now we need to prove it. Right? So why is this true? So okay, but first of all, I need to construct the polynomial P, and then I need to this P of A is 0 is just the same as saying P is in the ideal I. Right? So the proof is first of all how do you construct the polynomial. So first of all, notice by the Cayley-Hamilton theorem that there is at least one non-zero monic polynomial which such that. So okay, before that. So clearly this means that if you look at P min of A, well P min divides P min itself, so P min of A must be 0, right? So that's what we want to, of course we want to deduce as a consequence of our proof that P min itself also kills A, right? So well, let's start with at least one monic polynomial that does kill A, and there does exist such a polynomial. It's called the characteristic polynomial. So recall, so by Cayley-Hamilton, so PA of X, PA of A, sorry, or PA of X is a monic polynomial which kills A. Monic polynomial that kills A. There is at least one. Therefore, if the set is non-empty, I look at the set of monic polynomials that kill A, and this has degree n of degree n. So I look at the set of monic polynomials that kill A of degree at most n. That set is non-empty because the characteristic polynomial is in it. I look at the polynomial. I look at any polynomial inside that set of monic ones which has the smallest possible degree. Okay, the degree is n. So at most the degree is n. If there exists any polynomial of degree 1, then you are done. If not, if there exists a polynomial of degree 2, which is monic and non-zero, then you are done. If not, then if there exists something in 3 and so on. Until if there exists something of degree n minus 1, then you are done. And if even that polynomial doesn't exist, then at least then you look at the characteristic polynomial itself. It's a polynomial of degree n, it is monic, and it kills A. Okay. So so choose any. I'm saying, and the point is because I'm claiming it's unique. This any is not going. This any is really a trick. You just choose any polynomial, but the point is there is only one. Any monic polynomial P of X belongs to Fx of minimal degree this is getting increasingly pale. How is this not working? This is bad. I guess this thing was just like open. Ah, that's fine. Still. Change. Wasting pen. Fine. I think I have to use. Of degree is such that in fact let us give this polynomial a name, call it P min of minimal degree such that P min of A is 0. Okay? And the claim is that this polynomial satisfies this condition. The claim is this is the P min. Okay, how do you prove that? So okay, so clearly, so now if P min divides, so such that this happens, right? So now the moment this happens, if P min divides P, then clearly P of A is 0. The question is the other way. Then clearly this implication holds. The question is why the converse holds. That is the real sort of difficulty of the proof. So as for proving this, proving the converse, the forward arrow so okay, so suppose P of A is 0. What I do is the following. P of A has degree at least as big as P min, because P min is chosen to be of least degree. So divide P by P min. Okay, you can divide a polynomial to another, and this is where we use the Euclidean algorithm. There is a quotient and a remainder. So say P of A is 0, n cross n, using the Euclidean algorithm. Let us write P equals P min times Q plus R, where Qx, Rx are polynomials, of course. And what else do we know? We know that R is either 0 or the degree of R is strictly less than the degree of P min. It's either the 0 polynomial or degree of R less than the degree of P min. Okay? Great. Okay. Suppose the second thing, suppose R is non-zero. Okay, so that's where. Okay, what do we need to show? We need to show that if P of A is 0, then P min divides P. So that means that when you write this P equals P min times Q plus R, we want to show that R is 0. That means P min times some polynomial Q of X is P. That's exactly what we want. So, want to show there is no remainder. Okay, that's exactly what we need to show. Suppose not. It means that suppose R is non-zero and the degree is this. If not, so this is a proof by contradiction, not? Then Rx non-zero and degree of R less than degree P. Okay. Now let us evaluate R of A. But okay, that's not what. Let's say and. What is R? R is a polynomial. I can evaluate a polynomial on a square matrix. Let me do that. How much do I get? Well, R of A I can calculate is P of A minus this thing. P of A minus P min of A times Q of A. But you see, P of A was assumed to be 0, and P min of A, of course, is assumed to be 0. The 0 minus 0 times some matrix, and so this is literally the 0 matrix. So what do we get? We get a polynomial, a non-zero polynomial, whose degree is smaller than the smallest degree here, and which still kills 0. Of course, this polynomial, so is that violating this thing? Not exactly, because of this one word monic. But now that is very easy to fix, right? If a polynomial is non-zero, that means its top degree coefficient, whatever the degree is, the top degree coefficient has to be non-zero. That's the point of it. Dividing out by that, multiply by that scalar, which is 1 over, or the reciprocal of the top degree coefficient. Then you get a monic polynomial, right? So let alpha not equals 0 be the top degree, the leading or top degree term, leading or top degree coefficient, of R of X. So what I'm saying is alpha inverse R of X is monic. So alpha inverse R of X is monic. Okay, so just because I'm dividing by the top degree term. Not only that, if you multiply a scalar by R of A, then you get a scalar times A. So alpha inverse times 0, and alpha inverse times 0 is also 0. So you get, doctor, this is monic, it kills A. And the third point is that the degree of alpha inverse R, degree of any scalar multiple of a polynomial, is the same as the degree of the original polynomial, which is less than the degree of. So here you have a monic polynomial which kills A and has smaller degree. And that's a problem. So this is monic, comma, kills A, comma, and has strictly smaller degree, or I'll just say, and degree of alpha inverse times R of X is equal to this degree, and that degree of R is strictly less than the degree of P min. And that's a contradiction, right? The whole point was that P min was chosen to be the polynomial, any polynomial, which is monic, which kills A and has minimal degree. So how can you have something of a strictly smaller degree? That is not allowed. That is what one calls a contradiction. And the contradiction was to the part. So the contradiction means that this assumption that Rx is non-zero must be false. So Rx is 0, which means P min divides P. So I think I can just end it. Okay, so that is why there exists a minimal polynomial. It's not too long a proof, it's just less than 2 words, 1.5 words. But it's just the simple fact that there exists a minimal polynomial because you can use the Euclidean algorithm. So PID that I said that I know this because it's a PID. I actually proves this because it's a Euclidean domain, and so it's even the proof is sort of relatively straightforward from the fact that it's something much more stronger than a PID. It's a Euclidean domain. Okay, anything else I have to say here? Sorry, I never defined the minimal polynomial. So now let me define. This polynomial, the unique one, is called the minimal polynomial. Fine. So definition. This is getting bad now. The polynomial P min in the theorem is called the minimal polynomial of going because the polynomial in the theorem is called the minimal polynomial of A. Okay, but now the same exact proof. There was nowhere that I actually used the fact that A was a matrix. I could have repeated the same proof for any linear transformation from a vector, finite dimensional vector space to itself. Because for linear transformations, we also know the Cayley-Hamilton theorem. Okay, so as the above theorem and proof go through for I'll just say go through verbatim. Verbatim means word for word. For a linear transformation P without the choice of basis. Linear transformation P in lin V comma V with dimension of V finite. We can also similarly define the minimal polynomial of V, of T. And of course, it's the same thing. It's the same polynomial the moment you give T a basis. One defines. Let me maybe even give it a slight name. Let's call it, so sometimes I will, it's called and given by P min comma A of X x. Okay, so sometimes I want to put the a as well in the subscript, just to tell you which polynomial. And so similarly, one defines p min comma t of x. No difference. And of course, when you give t a basis, then you get the p min of t equals p min of t. But that's, I don't even know if I'll prove it. So for example, now because of the statement of the theorem, if there is any polynomial which kills a or which kills t, then p min must divide it. So corollary. So p min comma a of x divides as a polynomial the characteristic polynomial of x, and similarly p min of t. It's the same statement really. But that's what it says. Like p min, the minimal polynomial, of course, divides the characteristic polynomial. Great. Now let's do some examples of minimal polynomials. We've seen the statement, we've seen the theorem. Let us do some examples. And I think all my examples are going to be upper triangular. Yes. Yes. Okay, let's start with the identity matrix. What is the minimal polynomial of these? Well, so what you can say, so okay, of course you can guess what it is, and that's not too hard to guess either. But what you can even say is you can deduce what it is formally. So we know because of this corollary that the minimal polynomial divides the characteristic polynomial. Right? So what is the characteristic polynomial of a upper triangular matrix? It's the product of x minus the lambda i's on the diagonal, right? In this case, that's what happens. You get x minus 1 times x minus 1 times x minus 1 dot dot. So if you do x times identity minus this, you get x minus 1. So let me write this down. So PA of x is x minus 1 to the n. So by the corollary, P min of x is going to be x minus 1 raised to some factor. Okay. P min comma a of x is x minus 1 to the n for some n. And this divides that, so it is 0 less equals n less equals n. So now, because remember, it is monic, so it is a ratio, it's a factor of this. Well, there are only linear factors x minus 1 times x minus 1 and so on. So you can just take a few or many factors, and there is no extra coefficient outside because the polynomial is supposed to be monic. Leading coefficient is 1. So which m is it? Well, it can't be, okay, can it be 0? M equals 0 is just the polynomial p of x equals 1. 1 evaluated any matrix gives you the identity matrix. So it cannot be 0. Since x minus 1 to the 0 applied to A is just 1 applied to A, and that is the identity matrix, which is non-zero. Obviously. In any field, 1 does not equal 0. Gee, good. What about m equals 1? So x minus 1 applied to A, is exactly A minus identity. Aha, and look, that is exactly 0. And therefore that must be it, right? The lowest degree polynomial that's monic, well, the 0 degree polynomial did not work. The next lowest degree polynomial is the first degree polynomial. So this is a minimal polynomial. Implies P min comma identity matrix of x equals x minus 1. Okay, so that is how you answer this question. Okay, but now you can do more. So similarly, this is let's call this part A. Part B, I can look at A equals lambda times identity matrix. In that case, check the same exact way. Check that P min comma A of X. Any guesses? If you have guesses, then you can pause the video here and take a guess. And for those of you who just want to enjoy the show, this is exactly X minus lambda. Not very surprising. Okay, that's the first example. Now let's look at a couple others. The next one is also upper triangle. As I said, they're all upper triangular. The next one is the example of a Jordan block, 2x2 block. We will get to Jordan canonical theorem probably next week or maybe the week after that. The second example is that of a Jordan block. In this case, again, you can use the corollary. So PA, the characteristic polynomial is x minus lambda squared. Which means that P min is one of three possibilities. It is the polynomial 1 or x minus lambda or x minus lambda squared. It's one of them because those are all the factors of PA. Now, 1 again, it's never 1. The same reason, right? 1 evaluated in any matrix gives you the identity matrix, which is never 0. So 1 is no doubt. That's just. What about x minus lambda? Well, let's take a look. So if you look at x minus lambda applied to A, lambda means you have to do A minus lambda times identity. And as you can very well see, that this is not the 0 matrix. And therefore we are done. The first two are ruled out. Which means that P min of X, P min comma A is actually the characteristic polynomial itself. So sometimes it is true that it's the characteristic polynomial, sometimes it is not the characteristic polynomial, but a factor. Okay, so that's the second example. The third one, the third one is actually a good homework problem probably, but I won't give you. I want to write the third one down so you see how to write these proofs down. Okay, so I'll do that in a second. Let me drink some water. Okay, so the third example is a general, instead of saying the identity of lambda times identity, let me write down a general diagonal matrix. A equals lambda 1, lambda 2, lambda n, 0 and 0. A general diagonal matrix, all the lambda i's of course are in F, in the field. How do you answer this one? So what is it here? So the point is the following. Even if you have repeated eigenvalues or diagonal entries, the minimal polynomial doesn't care, right? If you have 5 lambda 1s, you do A minus lambda 1 times identity, all of them become 0. But the remaining guys don't become 0. Similarly, if you have say 5 lambda 1s and 3 lambda 2s, then A minus 5 identity will kill the first 5 entries, but not the last 3. A minus 2 identity will kill the last 3 entries, but not the first 5. So if you multiply them together, then that will kill both entries. And in fact, that turns out to be the minimal polynomial. So that's what you have to do. So let me write this down. So, okay. But so that may be a harder question to write down the answer to. But let me write down the answer when all of these are pairwise distinct. Pairwise distinct. Suppose I have different eigenvalues. Then if you look at each x, A minus lambda 1 times identity, that will have 0 in this coordinate and non-zero in the remaining guys. A minus lambda 2 times identity will have 0 in the second diagonal entry, non-zero in the remaining diagonal entries, and so on and so forth. So now the claim is again, once again, first of all, we know the characteristic polynomial is the product. So again, PA of x is the product of x minus lambda I goes from 1 to n, which means that the minimal polynomial is the product over some subset of 1 to n. I belongs to S, x minus lambda I, where S is a subset of 1 through n. S can be non-empty, S can be the full set. I claim that S is the full set whenever the lambdas are distinct. Okay, why is that so? The claim, as I said, so suppose S is not there. So the claim is that S is equal to 1, 2, and n. This is the proof. If not, then there is some element which is missing. Right? Suppose I is an element from 1 through n which is missing. Now look at the I comma I element of this matrix, of P of that matrix. Then look at P min of A, I comma I entry. What is this? This is the product of let's say I naught is not in S. Look at the I naught to I naught entry. It is the entries I in S. And now what is the, so because this is a diagonal matrix, any polynomial just evaluates P of lambda 1, P of lambda 2, P of lambda n, and zeros everywhere else. Right? So what is this thing? It is going to be the product of whatever that entry was. So P of lambda I. So okay, first of all, this is equal to P min of lambda I. Sorry, lambda I naught. And that is literally I in S, lambda I minus lambda I naught. But you see, because we said that I is in S and I naught is missing from this, these are, and the eigenvalues are pairwise distinct. So every term here is non-zero. Therefore, the product is non-zero. In a field, if you multiply two non-zero elements, you never get zero. Then this is non-zero. But on the other hand, P min of I mean, P min is a polynomial. So this is the I naught entry of the zero matrix. And that is just the zero scalar. On the one hand, you start with zero scalar. On the other hand, you get that scalar is non-zero. That's a contradiction, and the contradiction is to the fact that such an element exists in the first place. This contradiction implies that, implies the claim. This implies the claim. This shows the claim. And therefore, we get the minimal polynomial. Right? The claim was that the minimal polynomial is exactly the product over the elements of S, but now we are saying S is the full set, and therefore the minimal polynomial must be the characteristic polynomial. So, P min of E is equal to P. Okay, that's the third. Sorry, where is this? And the fourth one. That's fine. More than enough for now. Well, I'll do one more just for fun. This time A is basically two of those examples into lambda 1, lambda 0, lambda 1, 0, lambda. It's a 4 by 4 matrix. Okay, once again, the characteristic polynomial. x minus lambda to the fourth. So the minimal polynomial divides that, and then you can check that again. 1 of a is not 0. X minus lambda of a is not 0. That is clear because x minus lambda will kill off all these entries, but it will not touch the other two entries. But if you look at x minus lambda square, well, this is the point about block diagonal matrices. If you take any polynomial in that, then that's like saying you're taking the polynomials in each of the two matrices separately. So it's enough to evaluate x minus lambda square on this matrix and this matrix. And over here we saw that x minus lambda square kills this matrix. So it kills each of them. And so this is indeed equal to 0 here and 0. The other two entries were already 0 and 0, so that's fine. So we can see. Therefore, this is P. Okay, so that is what it is. So these are some examples. And so now let me first, so remember, So I told you that you should be able to define P min of T, and the fact that P min of T equals P min of A. Well, let me now prove that, and that's basically because, all you need to prove is that if two matrices are, so P min of T, so P min of T basically equals P min of A for some basis. Now, if I change my basis to a different one, what is the guarantee that P min of T won't equal a different polynomial, or P min of the conjugate? And that comes from the fact that if two matrices are conjugate, we already saw that the characteristic polynomials are the same. Now let me prove that their minimal polynomials are also the same. And where am I supposed to stop? Not here. This I will prove at the theorem. Yeah, I think I can state all of that. I can do all of that and then I will stop at the theorem. Yes. Okay. Maybe the next class I will go slightly longer. Today's class I'll cut slightly short. We are picking up after a long break, so let's go slowly. Okay, so lemma. If A and B, which are matrices in F to the n cross n, are conjugate, then their minimal polynomials are equal. P min comma A of x equals P min comma B of x. Okay, so proof. The proof is pretty clear, but maybe it uses one of it. I think I said a homework problem or something like that this time. I think I told you it was homework problem. Basically, the homework problem is the following. If you take any polynomial f, then if you look at f of, let's say, p, b, p inverse, this is the same as p times f of b of p inverse. This is the homework problem. I think it's even homework 10. So. Okay, so for every polynomial like that in f of x, if you evaluate on the conjugate, then that's the conjugate of the polynomial itself. That's not hard to prove, that's your homework problem. So now let us say that A and B are conjugate. So now say A equals P times B times P inverse. Let's compute P min A of this. Okay, so on the one hand, of course, I know this is 0. Let's compute P min B of A. Fine. Then let's just do this. I could do either one. Let's just do P min of B. Okay, so what is this? This is equal to P. So by this thing, it is first of all, let's start with, let's go slowly. So P min of B of P, B, P inverse. But now because of this homework business, this is equal to P times the polynomial itself, P min B of B times P inverse. But what is the minimum polynomial of B going to do to B? It is going to kill it. And therefore you just get the zero matrix. So even if you evaluate the minimum polynomial of B at the matrix A, you get 0. So what does that tell you by the theorem? By the theorem it says that the minimum polynomial of A must divide this polynomial because it kills it. So by the theorem, P min comma A divides P min comma B. But now A is a conjugate of B, therefore you got this. Exchange the arguments. You can say that B equals P inverse times A times P. So by symmetry, no, that's not say but, let's say now. Now, right? Similarly, B equals P inverse times A times P. So P min of, so you can check that P min of A of B 0. Yes, which in turn implies that P min of A divides, P min of B divides P min of A. So you have two polynomials, the ones for A and B, which both divide one another and which are both monic. And from this I will leave it to you to figure out why they are equal. I mean, basically all you have to say, so first of all, when something divides something else, you first of all know that degrees have to be less than this. And here the degrees are going the other. So degree of P min of A from here is less equals the degree of P min of B. Oops, I don't need this. On the other hand, so the less equals comes from the first point, and from this point the bigger equals comes. And therefore the degrees must be equal, and they are both monic, and therefore they must be the same. How can a monic polynomial of smallest possible degree divide another? Well, if you take the remainder, if you subtract the two, you get a strictly smaller degree polynomial, because the monic terms cancel out. You get a strictly smaller degree polynomial, which also kills A, which means it is divisible by a bigger degree polynomial. How can that happen unless the smaller degree polynomial is 0? Because the bigger degree polynomial had the minimal degree. Okay, so implies the degree is equal. And both are monic. And divide each other. And from this you can prove that they're equal. Because otherwise they would have to divide the difference, but the difference is a strictly smaller degree polynomial or 0 polynomial. It cannot be strictly smaller degree polynomial because the point was these are of minimal degree. Therefore it must be 0 polynomial. So the difference is the 0 polynomial, which means they are equal. Okay, so as a corollary to this, we get that P min of T is well defined because it doesn't matter which basis you choose. For all T belongs to linear, so for all linear transformations T from V to D, D finite dimension. Okay, so P min comma T of X is well defined because it doesn't matter which choice of basis you make. The matrices that turn out to be for T are conjugate to each other, and therefore are the same linear polynomial. Okay. Okay, now we already saw that the minimal polynomial, of course, has to divide the characteristic polynomial. We also saw examples where they're unequal, examples where they're equal. But in all the cases, somehow, yeah. But in all the cases, they seem to have the same roots. Okay? And that is not a coincidence. You can prove that the minimal polynomial always has the same roots as the characteristic polynomial. So let's prove that. I mean, it can be that there are neither of them has any roots at all. That can also be there. Like just take a rotation matrix. It has no roots, but its minimal polynomial is its characteristic polynomial. So that's a different matter. But you can let's just check that at least whatever roots there are, whether the empty set of roots or not, the roots are always the same. Well, one way is obvious, but the other way is what one has to prove, and that's not too bad either. Okay, so proposition. How many? Should I say for A or for T? Not for T. Say dim B is finite, T is a linear. So the same thing we say every single time. Then the characteristic polynomial and the minimal polynomial have the same set of roots. I'm not saying that the multiplicities are the same. That is the difference, right? So, for example, for the identity matrix, the characteristic polynomial was x minus 1 to the n. There are n roots, each of them equal to 1. For the minimal polynomial, it was x minus 1 to the 1. But the root was the same. Just the number of times it occurs is different. These have the same set of roots. Have the same roots. Of course, they may occur different number of times, and usually they do. Very good, very good. Proof. Say P min comma T of lambda equals 0. Suppose lambda is the root of the minimal polynomial, then obviously because the minimal polynomial divides the characteristic polynomial, that also works. This is obvious. It's the converse that we want to see. Conversely, suppose lambda is the root of the characteristic polynomial, which means it's an eigenvalue. So now we will actually use eigenvalues. Say Pt of lambda is 0, i.e. lambda is an eigenvalue of T. Now what do you do? I think I looked at the basis. So sorry, I should maybe have mentioned that. And the same roots, of course, maybe I should have said that here, which are the eigenvalues. Right? The roots of the characteristic polynomial are called eigenvalues. So the minimal polynomial has all the eigenvalues as roots. Not just some of them, but every single one of the eigenvalues occurs as a root. I'm not saying if that root occurs once or twice or as many times as in the characteristic. I'm not saying any of that, but they each occur at least once as a root of the minimal polynomial. Okay, so okay. So now, and this is sort of not hard. So let's see. So lambda's eigenvalue. Let's say with eigenvector v. So V is non-zero, right? So now let's look at PT of A. Sorry, PT of T. P min of T. So P min comma T, acting on T, of course, acting on V. And here is another homework problem we had set, right? If you take any eigenvector V of a transformation T, and you take any polynomial f of x and look at f of t acting on V, then V is still an eigenvector for f of t for this transformation, and the eigenvalue is that polynomial f applied to the eigenvalue lambda. So the eigenvalue here would be f of lambda times V, where f is of course here P min of V. So on the one hand, this is homework, I forget which homework, but this is P min comma T of lambda acting on V. Okay, so that is by homework problem. But on the other hand, what is P min of T acting on T? It's the minimal polynomial. So by definition, it kills the linear transformation. This is equal to the transformation 0 acting on V, which is the 0 vector in V. So a scalar multiple of this non-zero vector, V is of course an eigenvector, so V is non-zero. On the one hand, it's a scalar multiple of this polynomial of lambda times V. On the other hand, it is 0. Which multiple of a non-zero vector is a 0 vector? Precisely the 0 multiple, which means that this scalar must equal 0. So we have said one way, if the minimal polynomial has a root lambda, then the characteristic polynomial of course does. Conversely, if the characteristic polynomial has a root lambda, then the minimal polynomial has the same root. And therefore they have the same set of roots. Okay, so that's the next result. Now let us come to the theorem that I want to state. How much can I prove? Fine, let's just we're just finishing the 1 hour mark. So let's talk for 15 minutes more. Roughly. Okay. So what I want to prove for next, I'll keep it here. Maybe I'll keep it in blue and use it. I'll work on it next time. So T is okay. I'm not going to say this again, but theorem. Okay, so T from V to V as above. I'll just say as above, which means that V is finite dimensional, over some field, P is linear, and goes from V to V. Okay? T from V to V. And now suppose all the roots, sorry, this is the thing we had said about either you use an algebraically closed field or you just assume that all the roots of your, all the eigenvalues lie in the field. Okay? And say on, I'll actually, instead of saying that, what I want to really say, suppose the PT of A, PT of X can be factored into a product of linear factors. So all of them are roots, has n many roots in the field. So fact splits into a product of linear factors. Splits as a product of linear factors in F. Yeah. Okay. Then, so now I'm coming back to property, which is the property of being diagonalizable. Because we have talked about, so remember, we talked about AM and GM, right? I think we said that if all the roots lie in the field, then we have the AM GM equality to say that that's when the transformation is diagonalizable. Let's see, I have equality. Yeah. Right? The algebraic multiplicity must be equal to geometric multiplicity. Well, now here, that was in terms of the characteristic polynomial, right? Both were multiplicities of lambda. So algebraic was how many times lambda occurs as a root in the characteristic polynomial. Now here is the characterization. under the same assumption that all the roots of the characteristic polynomial lie in the field. In that case, we can now characterize the same property of being diagonalizable in terms of the minimal polynomial, namely that the minimal polynomial does not have repeated roots. Yes, there are no Jordan blocks which are larger than 1 by 1. Basically, that's what it really means, although we haven't studied the Jordan canonical form theorem yet. But if you have seen it before, then basically what this is saying is it's diagonalizable if and only if there are no non-trivial Jordan blocks. Every Jordan block is 1 by 1, therefore a diagonal matrix. T is diagonalizable. As usual, I will write diag apostrophe BLE. If and only if P min of T or comma T has no repeated roots. Okay, so P min of T had better have no repeated roots. That's if and only if something is diagonalizable. Okay, that is the theorem we are about to prove. As I said, I will prove it next time. I surely don't have enough time today. So I will just go next time. So, but today I'll prove if I can. Maybe I'll state a lemma and stop. It's not, the lemma itself won't take too long, but I somehow don't have time today, unfortunately. Let's maybe I'll try. Let's see. So the proof uses. It's a weird looking lemma. Okay, I mean, it's completely non-intuitive. Like the previous result and so on. These are very natural things to try out. This lemma, on the other hand, is not, unfortunately, but it is as it happens. Sometimes it happens. So it's okay. T from B to B as above. Okay. Wow, what happened to this pen suddenly? Well, that's good if the pen is working. Okay, so suppose there are pairwise distinct eigenvalues basically. Say there exists lambda 1, lambda k in F, pairwise distinct. And what one calls as projection operators, so idempotent operators, basically EI linear transformations, so and linear maps. EI meaning again E1, E2, Ek, from V to V, such that or satisfying three conditions. One, which one is one? It's I think T is equal to summation. Yeah. The map T is equal to the linear combination I goes from 1 to k, lambda I, ei. 2. The identity map is the summation from I goes from 1 to k, ei. E1 plus E2 plus En. And 3, I think ei, ej is 0. Yeah. The 0, if you compose any two of these linear maps, okay, let me just say it here. EI, EJ is a zero transformation for all I not equals 0. Suppose I have these three. So suppose I have a set of scalars and a set of linear maps such that T is the linear combination of those maps, identity is just the addition of those maps, and those maps kill each other. Meaning, if you compose two such transformations, you always get 0. Then the claim is that the T is diagonalizable, and lambda 1 to lambda k are all the eigenvalues. So let me use a different pen. Then lambda 1 to lambda k are all the eigenvalues. Okay, so that's what it is. Okay, I think no, this is a complicated proof. It may even take half an hour to prove. So once this proof is done, then the remaining part of the theorem is, yeah, overall it will take less than half. Overall it will take about half an hour to prove. So maybe this is not a bad point to stop. I know it's a much shorter class, maybe like 70 minutes instead of 80. Yeah, something like that, I think. But okay, that's fine. Today is a shorter class, I guess. Any of the pens are not working. I need a better pen. So let's stop today and then, yeah. So next time what I want to do is I want to start by proving this lemma. I will not erase the theorem, but I will, I'll prove it on that board and then I will erase the lemma part. By the way, so one thing I should point out. So you are of course allowed to use either the theorem or the lemma in homework 10 because we have stated it in class. If you need to, you can use it. I'm not saying you will need to, but if you need to, you can use it. Okay? And similarly, all the previous results obviously are fair game to use for the homework. Okay, so I will just erase this and then stop the recording. And so the next lecture again, of course, is on Tuesday. And today's homework is on tomorrow's homework. This week's homework is due next Thursday, as always. Okay, so we will start next time, as I said, by proving the lemma, then proving the theorem, and then moving on.